states.
So it's infimum taken over Q.
This is a standard definition. You can see it's also in the entanglement entropy defined by Metral and so in the 90s, in the 98, and you can find it in various settings, in green, blue, and it's really often. And if you change, if you flip the argument, you have it in large deviation theory.
Because I would usually find infimum of P, variant P, but here is infimum of Q.
Yeah.
So
now, please, the argument P is fixed. I want to know how much interaction of order K is there. Actually, I missed the point because it's the interaction order of K, but it's the exact point. If I measure the distance of states which have the most interaction K, then I measure the correlation which have interaction K plus 1 or larger. Yeah. This is a definition, it's well known. Linden has used it. Linden and I think, I'm not sure if it was Book et al. In 2002 defined and used and looked at this problem in a different setting, which I show you later. They looked at this definition, which comes here. But I can go step by step through it. And Su also used it, and Amari has used it, so it's very, very well known. This approach here.
No, I understand. Just the interesting that that P and Q, yeah. So in the definition of distance P and P over Q, and so the infimum has taken over the second argument Q, not over P. So
I see the point.
Well, the second point. If you want to find so the infimum would be, for example, you take the derivative equal to B0, for example. So that would be the minimum.
You want me to calculate the minimum? I can do it by myself because of some theorems. You should, which you know very well, like the Pythagorean theorem, which helps you to compute the minimum. You don't need to make a derivative. Okay.
But, I'm just curious, I guess, here.
Yeah. So this is a definition used by Amari, for example. So it quantifies the correlations in a probability distribution which is caused by interactions of K plus 1 and larger. Okay. So now this is a projection theorem by Amari, which I will not explain to you, but I just tell you that it can be used in the proof. This maximum entropy state which we have used earlier, which specifies the marginal, which from the marginal specifies a global state. Is the point where the infimum is assumed, is achieved. And you can rewrite this by the Pythagorean theorem as a difference of KL divergences from the uniform distribution, from the Laplace distribution, and then we turn things around and have here the difference of Shannon entropies. You can always for any Gibbs family, the divergence, you can always compute it as a difference of Shannon entropies. And in the quantum case, you can always write the Megaki relative entropy from an exponential family as a difference of von Neumann entropies. And this is it. Then you can decompose, rewrite this slightly. This is actually the picture for it. You have your P, you project it down to the maximum entropy state, and then here's the Laplace state. And then you get your formula. And this here was introduced in 2002 by Linden and colleagues, and later by Su in condensed matter physics. And what they have done, they have interpreted this as the correlations which are created by interactions of exactly k bodies. And this gives you a decomposition of information. This is IP, the total information. Many of you will know it. You sum over all particles and you compute the one particle entropy, subtract the whole one, and you can write it like this. This is the product distribution which we have seen on the first slide, and then you have a decomposition into this irreducible correlations by Linden and Su. So this far is not bad. this formula that you can do this, decomposition depends actually on this construction of Pythagorean theorem and projection theorem, and this was done by Amari in 2002 for probability distribution of full support. Then later in 2011 was done for probability distribution of arbitrary support by I. Etsu has done the same construction for density matrices in quantum setting in 2008, and we have done a proof for arbitrary density matrices of arbitrary support. And the fancy thing is, this arbitrary support is a very interesting thing physically, because it means you can handle thermal states at zero temperature. So this, I did not realize this, or I did not emphasize it. I just ignored it for several days. But this is, in my opinion, very exciting. It gives you connections to the topological quantum order, to adiabatic quantum computation, and quantum phase transitions. There was a paper by Chen recently, which I have written here. So this is, I guess, I wanted to show you about the maximizers. This is for the minimizers. No, but the minimizer. Yeah. This is true. The distance is minimized and gives you the higher order correlation. Distance from low order states is equal higher order interaction. But then you use this method, this measure TK, which quantifies the higher order correlation, and then you want to maximize this measure by itself. This is what I announced in the early beginning of the talk as an info-max principle in neuroscience, where systems tend to maximize structured correlations. They want to, and then it's interesting what comes out. Which distributions are local maximizers, for example, of such a correlation measure, the distance from the k-body interaction distributions. And then it turns out, this is a result by I should have written it here. I will write it here. DKP is max? Okay. No. Is infinite. Local max. Then this implies that a support the restriction is equal, smaller equal the dimension of the probability set of the model plus 1. And in the quantum case, this is classical probability distribution, and in the quantum case, it implies that the support of P smaller equals the square root of dimension 8k plus 1. The difference came from, this is done by I in his PhD dissertation, 2001, I guess. And this was proved by ourselves lately. I think I proved 2009. And this depends because the algebra of observables in the quantum setting of n levels has dimension n classically, or n squared economy. So in quantum we have a density matrix, which is the n times n matrix. This dimension difference is here square root, and if you evaluate it here for the total information I, the difference from the exponential family of order 1 interactions or product families, then you get so P smaller equal n number of bits plus 1, and this is classical, In quantum, you get the bound 3n plus 1. And this asymptotically means that we have a different scale of size of your maximum. Anyway, this is an exponential reduction. Classically, also, this is much larger than 2 to the n, which is the whole space. Yes, you have an exponential reduction for local maxima. This is very strong. It means that a system which maximizes interaction in the sense of correlation has a very, very exponentially reduced support. And quantum mechanical, you have still a better reduction. What it means quantum mechanical somehow that states of high interaction, of high correlation, they have still less chaos in the distributions.
It depends how you define chaos.
Yes, they are more ordered. They have a smaller support. Exactly in this sense.
Okay, in this sense.
Okay, thank you very much. Okay, thank you.
If we want to continue, I don't know, I think we've already been here for a while. We can maybe move the discussion to coffee. Yeah. we sort of can go to the corner and have coffee. So we had a very different talks today. It was quite interesting. I have to say, a lot of things I haven't understood in the second talk, so I have to ask you maybe for a reference. If you have written this down already.
The paper is not accepted. We have submitted it in June, and it has many different aspects of theory. For example, if you remember this factorizability, it's not easy. So many people from discrete mathematics may know it, but people from quantum mechanics do not know it, and
vice versa. Yes. That's always a problem of falling between the and
actually this part of factorization would be easier to explain it in bits, as I did today. In this paper we made it very general for hierarchical models, which is not needed. Maybe we have to simplify it later. Okay.
But by the way, this we'll talk about this last time. Right, anybody is going to the pub today then? You know, that's there is a pub not far, that's Greyhound pub. And a lot of people usually go there at 5 o'clock, but I don't know, you'll see.
Yeah, we have to go there. You want to join?
Yeah,